Well, we wanted to talk about what's hot. Well, that's about as hot as it gets right now, what's going on right now. We've been very anxious about load transfer for a long time. It's always been one of our most anticipated stages. We actually think once we're on the other side of load transfer, most of our risk is behind us, which is really great. We've been monitoring statistically, probabilistically, financially and schedule-wise, what are the greatest threats. So I'm really anxious to have this behind us. The other thing that's hot is quality. Always has been, is, and always will be. Okay, and I wanted to share with you, what's hot about quality. Well, first of all, we take a lot of our guidance on that from a lot of different codes. Okay, codes of construction practice, American standards for ASTM for testing and materials, the welding codes, bridge design specifications, and our standard specifications. Okay, so we start with those. Next slide. Okay, concrete. I want to talk about concrete a little bit, right? Materials, it's always fundamental. Next slide. We pump a lot of concrete in our bridges. Doesn't matter if they're concrete or steel bridges. We put concrete on timber bridges, right? So we do a lot of concrete work in California Department of Transportation. This is a shot of concrete going in. This is what a typical crew looks like when they're putting in. This is the end of a pump truck. So this concrete usually is pumped in place with a very large truck. Next slide. This is a side view. It kind of gives you a picture. This is the end of that pump truck. It's an articulated, usually 3 or 4 arm system. And usually there's a whole series of trucks feeding concrete in. Next slide. This is a shot of those trucks. You see the tower in the background. Sometimes they're even side by side. A lot of action right here. Next slide. If you get in a little closer, this is the concrete chute, or this is the chute coming out of the back of the concrete truck. It's going right into the agitating area of the pump truck. And it's important that you get a chance to see what we see when we're out there. We see this concrete coming out. And that's an important thing. We're going to show you some tests here about concrete, but one of the most important things is an engineer's or a technician's eyes. Okay? If you work inspecting concrete for about, say, a year, you're going to have experience or a background to be able to look at and go, there's something strange here. And of course, that's when you right away say, I want samples right here. Okay? So eyes are first. And here's an analogy to that. Have you ever known anybody who's a really good baker and they bake up a cake mix? And good bakers can look at the cake mix and go, it's too runny or it's too thick. Well, you can do the same thing with concrete. So that's step number 1. It's a simple one, but it's one, right? You get a chance to see it. Next slide. Okay, here's a shot of the action that's going on. The concrete truck, the end of the chute. And here's one of our inspectors. And you see him looking at something. Next slide. We always have an inspector right there. Oh, we missed one. Back slide. Oh, here we go. No, that's good. That's good. That's good. Down here in the right corner, this man right here is looking at something right here on the end of the pump truck arm. This is what he's looking at. It's the batch tags. Every single truck that comes in, we have printouts of exactly the batch that went in. We know exactly the recipe that went in. All the chemicals, the weights, etc. We know the mix. And we've prepared practice mixes up front. So long before the concrete ever comes, right, we're inspecting at the batch plant. We're also trial batching. We like to mix up ahead of time, verify that the concrete, let it harden up, do testing on it, all kinds of different testing on it. We make sure before we get to this place, we know what this concrete mix is like and is it going to have all the attributes and the characteristics that we need. Then we also make sure that the stuff that the recipe that we ordered, that's the stuff that we get. This is an example that we keep all of these. Okay, this also tells us when the truck comes out and how many times the drum is turned. Next slide. Then right at that spot, we have our experts, our inspectors, some engineers, some technicians, and they actually do field tests on the wet concrete. There's a variety of tests that are standard across the industry in doing that. Here's a shot of that process that's going on. Next slide. Okay, then we also go in the laboratory, right? And we actually test once the concrete comes up to strength, and we do that test. Now, I believe we have a video.
Caltrans calls it the Wybitz Phase 2 concrete pour, and spokesman Bart Ney will take you on a tour of this massive project for the new Bay Bridge.
All right, we're right in the middle of this concrete pour. MCM Construction, our prime contractor, and Central Concrete and Supply are managing up to 12 trucks on the bridge at one time so that the concrete keeps flowing throughout the entire pour. The Bay Bridge from Oakland to San Francisco is almost 8 miles long. In our seismic retrofit of this job, there are several different structures that we've had to build in order to bring the entire project, the entire bridge, up to current seismic safety standards. Today we're going to look at our Yerba Buena Island transition. This is the part of the bridge where we take the new bridge that's been constructed with parallel traffic, side by side, and reorient that into a double-deck configuration so that our traffic can go through the largest man-made bore tunnel on Earth, the Yerba Buena Island Tunnel. It's a challenge because we are now sitting in exactly the same footprint as the original Bay Bridge was constructed. Caltrans had to place this detour back in 2009 that took traffic out of the way so that we could demolish the old approach from the Bay Bridge and put our new bridge in the exact same footprint. So that's one of the biggest things that we've had to do with the Bay Bridge. Keep traffic running, keep 280,000 vehicles moving while we put massive structures like this one in the exact same place as the old bridge used to be. Today in particular, we're doing an 1,100 cubic yard concrete pour. And as we're moving forward with this project, you can see how much progress we've made. Literally the upper deck above my head is going to be the new westbound transition, bringing traffic to the top part of the tunnel. And what I'm standing on here is where we're pouring concrete today. This is our eastbound approach heading toward what will be the world's largest self-anchored suspension bridge. One of the special things that we're doing today in this large concrete pour is we're putting our tining in, the grooving that's on the freeway that keeps your car on the structure. We're putting that in longitudinally, and what that means is we're cutting these grooves in along the same route that the tires go across the bridge. It brings the amount of freeway noise significantly lower.
What seems like a recurring, endless line of cement trucks deliver their loads to 2 pumping stations. The nearly $744,000 pour is going like clockwork until something goes wrong.
The pump over here has broken down. The main drive shaft broke, and the problem with that is that everything on the pump works off that shaft. So MCM is going to bring another pump up on the bridge. In the meantime, this one can move a little bit to continue to service the pour.
These portable boom pumps each cost more than $1 million. They are only used on major jobs. There aren't a lot of them, and one has to be found immediately, or the pour could be endangered.
So the danger here when something like this occurs is that you would run out of time and create a cold joint.
A cold joint is where the already placed concrete starts to harden, and then fresh concrete is placed beside it. The broken unit is at the end of the pour, and the unit that is still working is now the furthest away, its arms stretched as far as it can go, 190 feet.
I'm trying to keep the pour going, get under that boom and pour some more.
Tom Brower is like an air traffic controller. He operates the boom by remote control. His years of experience are being tested. There is a mid-air traffic jam with little room to maneuver. Brower and his partner's faces are taut with concentration.
Come down with your B, leave your A up.
This pump has articulated itself out as far as it can possibly be so that it can pour as much of the area while we're bringing the new pump in.
Brower succeeds, and fortunately, as a contingency requirement, the contractor, MCM, is required to have extra equipment staged nearby on standby. That unit is in Oakland.
If they need CHP, we should be able to arrange that.
The Putzmeister 631, built in Wisconsin, owned by Associated Concrete Pumping, comes to the rescue.
Oh, I am relieved, yeah. They worked their way through it, right?
As the machine is frantically set up, the waiting concrete mix from each concrete truck is tested by Brandon Young.
He's an inspector for Caltrans, and he's the one that's monitoring the concrete to make sure that we don't have to reject any of the batches. But with that little bit of a slowdown, we had to make sure that the concrete didn't set up. So a number of factors go into determining whether a mix is good. This one was fine because although the temperature is getting higher, there's still plenty of slump. there's an admixture into this that's actually keeping the temperature low so that it can make it through the entire pour and then set up as it was designed to.
The samples are weighed, tested for the consistency of the concrete and its wetness. The samples of each truck are always saved for the record.
We had to keep looking at the concrete because it had to sit for a little while they did the replacement. And the test came out okay. What's in the camera?
5 hours later, trucks are still lining up, and the pour, now almost a football field in length, is nearly complete. The eastbound and westbound lane structures that will carry traffic starting Labor Day weekend 2013 are firm reality. The pour will cure for a week, and then we'll show you the next step in making it even stronger. These giant spools of steel cable will be used in post-tensioning of the concrete. That story to be continued. On the Yerba Buena transition structure, Mark Jones reporting.
Cylinders are samples are received from the field and brought into the lab and processed. We strip them from their molds. Paperwork's also received with each specimen, giving us a break date and a fabrication date, age at which they're to be tested. So it's a plastic cylinder, meaning they also have certain requirements that they need to meet. So. So here's a concrete test specimen from the field. Once that takes place, we transfer information from the paperwork to the cylinder, and then this information will also be entered in our database and scheduled for breaking. This piece of paper that comes to us from the field giving us date cast and age at which they want it broke at. So we'll get a contract number and some other pertinent information on here. It just helps us to track these. At this time, we'd take a look at the ends of the cylinders and see if they need any modification to make them meet the requirements before we're able to sulfur cap them. And these cylinders do need a little bit of work, so we're going to take them over to our concrete saw and prep them before we cap them. That gives us the kind of end we're looking for prior to the capping process. These particular cylinders aren't going to be broke until March 12th, so we'll put them in the fog room and cure them until March 12th. From the fog room, we're set up for 30 days out. We'll take these, and we don't have, as far as the date, these will have to be put on a hold rack until they're able to fall into sequence into our on our racks here. So they're just those cylinders will be kept into the fog room until the break date. Sometimes we get breaks in here that are required to be broke in 56 days. Therefore, they would just go to a hold rack in here in the fog room until they're transferred into sequence. They all have a requirement for curing, and at this time it's 100% humidity, and you can achieve that in a water bath. But there are temperature requirements and there are moisture requirements. Okay, after saw cutting, then the cylinders are ready to be sulfur capped. Well, we have requirements for the ends of the cylinders that they need to meet, and they need to be planed to within 0.02 of an inch and 6 inches. So the sulfur capping process provides us with those ends meeting those requirements. This is just a lubricant to make sure that the cap comes out. This is our sulfur capping compound. It's kept at a temperature from between 260 degrees and 290 degrees. Dries extremely fast and gives us the ends that we're looking for on the cylinders. We're just removing the moisture from the surface. So we're drying the surfaces that need to be capped. This is the jig that we use. The cylinder will go up against these guides, and this keeps the cylinder perpendicular to within the requirements that we need. And the cylinder will be placed into the capping compound, and then we'll show you the ends. Just takes a couple minutes for this to dry, and we'll be able to remove it. We'll cap the other end, and then we'll check the ends for plainness. Now, as you see, we've got a plain surface here. You want to make sure that there's no voids underneath your capping compound. We take this precise measuring tool here, and you tap it, and you're listening for a hollow or a void that you may get. If you get a nice ringing or a ping like that, then you have no voids. The surface of the capping compound, or the end of the cylinder, is required to be planed to within 0.02 of an inch and 6 inches. So you take your straight edge, you take a feeler gauge, 0.02 of an inch, and just check to make sure that it meets those requirements. If this was a bad cap, then of course that feeler gauge would slide under there.
But it's nice and flat.
It's nice and flat. We check it in several different locations throughout, around the cylinder. So this would be a good cap. All right, once the cylinder sulfur capping compound is cured the required amount of time, it's then loaded into the testing machine. Centered in the testing machine. The table's coming up. We'll apply just a very slight load to it and seat the sample. Okay, it's just touched down. I want to make sure that this is all seated in here, centered. Doors closed. And we will transfer the data from the cylinder. All the data has been entered into the machine. We're going to start the test now. We will get a graph here, graphing the load that the cylinder is receiving right now. If you're braking at 10,000 PSI, if you're loading at the required load rate, it could take 3 or 4 minutes to brake. We're already loaded this too. If you look here, this will give you the pound load that the cylinder is receiving. So we're up at 137,000 pounds. Using the cross-sectional area, you divide the total load by that, and it'll give you pounds per square inch, which we're already up to about 5,400 PSI. The load that's on that right now is 200,000 pounds and about 7,000 PSI. We're at 230,000 pound load and 8,200 PSI.
And about 10 is when you think?
That's, right around in there. So. At this point, it's kind of hard to say. In the 16 years I've been here, we've had probably 5 different instances where we actually had to abort the test because it was going to exceed the capacity of the machine. So. Okay, we're up to 300,000 pounds. There you go. So,
You guys didn't tell me what I hear.
this was 302,190 pound load with a result of 10,688 PSI. We have to note the type of break that this occurred, and we have 6 different breaks. A nice conical break, you could get a columnar break, you can get just a split, but that's also another piece of information that they want on the report. This is going to be like a type 4 break. The result for this is 10,688 PSI. The results now will be pulled from this machine, entered into our database, and then sent out via email to the resident engineers or the structure reps on the job. For the purpose of this demonstration, we'll be opening the protective door, and we will start the press, start the test, and all walk away to a safe distance, and then the break will be recorded. We're at 8,500.
Okay, the next material that's very common to us is reinforcing steel. There's a nice example that you can actually pick up that's out in the foyer. However, we've got one of our larger ones right here, number 18 bar. It's actually the large bar that you're actually going to see broken in just a little while. Next slide, please. Okay, Caltrans, we use a lot of reinforcing steel. Okay? The reason we use structural steel, reinforcing steel, commonly called rebar, is because concrete is very, very good in compression. Rock can carry a lot of weight on it, a lot of weight, only when it's in compression. But concrete's not very good in tension when you try to pull it apart. It breaks at just a tiny fraction of its compressive strengths. So what we do is we build a new type of hybrid kind of material called reinforced concrete, where when you get bending, and I'll show you bending. This is a tool I like to use when I teach statics. It's a spring. This is tension. This is compression. And this is bending. So in a simple bend, the top part, where the spring elements open up, okay, the rock would break and open up. Down at the bottom, where the spring elements go into compression. So bending is tension on one side, compression on the other. Okay, concrete won't do that very well. So if we put reinforcing steel, things that are 50,000, 60,000 pounds per square inch of steel, okay, we can put steel where elements go into tension, let the concrete be very strong in compression, so we get a new hybrid kind of material.
Thanks.
Okay, this is a shot at Hinge K. Next slide. This is a shot of a deck. This happens to be Yerba Buena Island. You see a lot of reinforcing steel. You'll also see some pre-stressing ducts, and I'll be talking about that in just a little while. Next slide. Okay, here there's some girders. So you see that around a reinforced concrete structure, or even a pre-stressed concrete structure, you still have a lot of reinforcing steel. So it's an important part of our job. And we have a lot of it in our columns, foundations too. Next slide. And sometimes we have to couple them. Sometimes you can only bring a piece of steel on a site about maybe 60 feet long, because that's how long a truck is. Anything longer than that, it's not really transportable. It's not going to be economical. So sometimes when you need pieces of steel more than 60 feet long, we end up having to connect them, and we use couplers. Next slide. Okay, we test those too. Put them in a machine. Next slide. And then we break them. Now I think we've got a video, about a 1-minute video. This is exactly this number 18 bar that's down on the stage, if anybody wants to see it afterwards. And one thing that's important to note is we made sure that this coupler was actually stronger than the bar. Okay? So that's our criteria. Next slide. Okay, I want to talk a little bit about pre-stressing. Next slide. Now, what is pre-stressing? Well, I'm going to have to put the microphone down, and we'll tell you what. Thank you. Okay, this is a shot of the Skyway when it's cantilevered out. Now, cantilevered means it's basically only being supported on one end, and it wants to sag down. And that means there's going to be tension on the top and compression on the bottom. And these kinds of spans that are very, very long, regular reinforcing steel that's, say, 50, 60,000 pounds per square inch, it's not going to be enough. Because what we want to do is, if the concrete starts to do this, it's going to break or it's going to open up, and then salt, water, et cetera, is going to get in there. So we need it to be tight. So what we do is we don't just take reinforcing steel, we bring in pre-stressing steel. And there's a sample out in the foyer. There's also one over here that either you've looked at or you can inspect or touch here. What we do is we take this pre-stressing steel, and it can be post-tensioned or pre-tensioned, two different variations of its use. But that steel is 5 times stronger than regular steel. Okay? Regular plate steel is like 50,000 pounds per square inch. Pre-stressing steel is 270,000 pounds per square inch. Okay? So it's really, really strong. And what we do is we put that steel in the top to bring it back. Okay? Now, this is if it's cantilevered. So on this structure, where it's cantilevered, we're going to have a lot of pre-stressing steel up at the top, and we call them cantilever tendons. Now, if you have a typical beam, where you've got a column of my left hand, column on my right hand, and it's supported like this, and you get bending, and say there's a truck in the middle, now the tension is on the bottom of the beam, and the top is in compression. Okay? So if you're in the middle of a structure, and it's not cantilevered, but it's supported by columns on both sides, then now you need the pre-stressing. It's a long span bridge. Now you need the pre-stressing on the bottom. So sometimes we need to drape or place pre-stressing strands in different locations depending on the type of bridge and how it was erected. Okay? So that's really what that's doing. Next slide. Okay, this is a shot of a cross section. Happens to be Yerba Buena Island. And this is the end of a frame. And all of these holes, if you will, what they are is they're the end of basically tunnels. We call them pre-stressing ducts. Okay? And these go on for the length of a bridge. And sometimes they're high, where they need to be high for a cantilever tendon. Okay? And sometimes they come down low, where they need to be if they're on out in the middle of a span. So we place these where they need to go. Then we use this kind of pre-stressing strand, and we place them inside, sometimes 1, sometimes 2, sometimes 4, sometimes 13, sometimes 26, sometimes 37, however many we need. Each strand has 7 wires. Okay, a tendon has as many strands as the designer needs to put in. Okay, so here with this slide, you can see we have a lot of pre-stressing in certain bridges. Okay, and the Bay Bridge, because it has such long spans, we have a lot of pre-stressing. Next slide. Okay, here's a shot of the first few pre-stressing ducts going in. So as the girders are built, the rebar, as they're first placed, the bottom ones go in first. Next slide. Okay. Then as the rest of the bridge gets constructed, then a lot more tendon ducts go in. Okay, as you move up the girders. Next slide. Okay, now this is a shot if you're standing on top of a girder in construction looking down on it. Okay, so you see we have a lot of these in every single girder on a long span bridge. So there's a lot of it. Next slide. Okay, now I want to get back to Joe Nicoletti. And again, here's a challenge that we faced, and I want to walk you through what we did. We found on the Skyway that there were some vents, grouting vents, that had broken off. Now, grouting vents, eventually, we put high strength grout inside those ducts to fill up all the voids. The tendons, the pre-stressing tendons, don't completely fill those ducts. So once we're done pre-stressing and erecting the structure and loading it up, we actually fill those ducts with grout. And we do it through the vents, but we also let the air out through those vents, but they need to be capped. What we found out was some trucks had probably run over them and they had broken off. And then when it rained, water got inside those ducts. Water and steel don't work very well. Okay. Next slide. So as soon as we discovered this, the first thing we did is we put together a team. We brought together all the elements of a team that we needed to evaluate and figure out exactly what we needed to do. First thing you have to do is get as smart as you possibly can about it. And what we did is we went to areas where we could get access to those. Okay, kind of like if you have a problem with your knee, you're not going to want to open up your leg, you just want to open up a little hole. So what we did is we went to strategic locations where we knew we could get access to it. So here's a shot of an opening at the top of a deck. Next slide. Now we're going to zoom in on it a little bit so you can actually see in this opening, you can see those pre-stressing strands, right? And what we did is we brought in new technology to look into this. Okay, we brought in some new technology, and what I'd like to do is ask Jason to come up, and if we can turn on the lights, I'd like you to see how we looked into this to evaluate, because what we needed to do was find out what's going on.
What I have in my hand here is a digital borescope. It's a lot like a high-end, high-speed digital camera that. Thanks, sir. Are you able to see inside that? Yeah, bring it up a little. All right. Okay. You guys can see on the screen, it's going right inside the vent tube that we have right here. You can actually see the strand right down inside. Go ahead and articulate the camera head, and we're able to get down inside the tube now. And now we're going to go ahead and run it down. So my right is the direction that it's facing. You're able to see right down this tube. We can see the condition that the strand is in. We can see if there's anything in there, water, rust, or any other type of material. One of the things I'd like to do real quick is have somebody come up and try this themselves. Can I have a volunteer?
And sir, your name is?
Bill Roan.
Oh, Bill Roan. So you have some history with the Bay Bridge, huh?
A little bit.
So let's head back over here. Pretty much in the same. Okay, so we're just going to go right through this insertion tube. Go ahead and handle it.
Okay, Jason, here you go.
Thank you, sir. What we have here is a screen.
I need to see what's going on.
Oh, sorry.
There we go, thanks.
Go ahead and take that with your hand.
Okay.
You have the insertion tube with this hand. It's a 6.5 millimeter digital camera with LED light. Just go ahead and slide it right down that insertion tube, or the insertion tube down. I got this. You got it? Yep. Thank you, sir. You can go ahead and see how you have that hole right there at the bottom of the vent tube, and you can see that. You can see the tins down inside.
Just lost.
You got to pull it back a little bit, and then you have this little thumb drive right here that you can articulate that camera head around. So you kind of drive it where you need it to go. So you need to pull it back just a little bit.
Okay, so the light is right there.
The light is right there.
Which direction is
I'm not sure. I'm not
Oh,
pulling
okay.
it up. Put it in. Let me go ahead and get you set up here real quick.
Okay.
So I have a home button that brings me right back to top dead or bottom dead center.
Okay, so
Okay.
pull
So
it back.
you pull it back. You see that hole right there?
Yes.
Just go ahead and drive your thumb over the opposite direction that you're going. It's kind of complicated,
Yes,
right?
it is. It's like flying a helicopter.
Yeah, kind of.
I lost it. I just crashed.
I actually train people on how to use this equipment for the state also, so you're doing fine.
I'm pretty hopeless right now.
So what you do, once you get to that point, basically you articulate it over and you slide it right in and it goes over where it needs to go.
So you're not going to hire me right now?
And you could record this, right? You can
That's correct.
videotape it and create
That is
archive.
correct. We actually have the ability to record this and save it for document purposes and writing reports and giving Dr. Moran the information that he needs to make his decisions.
I'm going to ask for one more borescope example where Jason's going to investigate going down the end to inspect the very end of an anchorage of a pre-stressing system. This is an anchorage system of a common pre-stressing system.
I'm just driving the insertion tube right down.
That is great. Thank you. I hope when you leave, if you're interested, we've got several elements of anchorages. Now, I want to make sure you appreciate what this provides. To me, what Jason did when we were struggling with this particular challenge, he gave us insight. So imagine you have a knee problem, and you need to know what's going on. This is basically the kind of scope that a doctor uses to go inside and evaluate, collect information on a knee. And then you can make decisions. You decide, do you take it out? Do you put something else in? What do you do? Information is always the best thing to do to get to guide people in making decisions. And this was just fantastic. And actually, Jason, if I remember right, when this was purchased, you were the first person in the United States at a DOT that had this equipment. Is that right? So, a first. Now, if we can go, okay, very good. Thank you. This is the next slide I wanted to go to. That kind of information that Jason made available to everybody, this is the kind of thing that we would see, okay? Up top, this is what we saw in most of the overwhelming, most of the amount of steel. We literally took thousands of recorded photographs. Down below, you see just a little bit of surface discoloration. And up at the top right, you start to see, and I want to use a laser pointer. You still see the surface of the steel, okay? But you see this material. Now, some of this material is actually the product of a chemical reaction with protective powder that we put inside these ducts because there's always moisture, right? If you build anything in the Bay Area, water's going to get everywhere. Okay? There's nothing that you build that doesn't have moisture somewhere. Okay? So what we do sometimes is we proactively put in chemicals that react with water. And when you see the steel, it's very, very smooth, and then you see you see clearly surfaces of the steel, and you see some of this. It's really not the steel oxidizing. It's really the chemical reaction between the moisture and the actual protective powders that we put in. And then down below in the bottom right, you actually see some of the worst stuff that we saw. This is what was termed moderate corrosion. Okay? Now, I also want to make sure I highlight, I think I've actually got it up here, this is magnified, okay? This tool allows us to magnify tremendously so we don't miss anything, right? So it does look pretty exciting, okay? Next slide. And it draws concern when you first see it. But let's get a comparison real fast here. This is from the borescope, and again, you look at it and you go, whoa, this is the same tendon when you lay it out and you just look at it without the magnification, right? And then this one, same tendon, it was cleaned up and kind of unwound, right? And this is what it looks like, okay? Next slide. Then we took some of those wires, because when we saw some of this, when we see pitting, that is a change of surface, we get concerned about stress concentrations. And in some cases, we said, get it out. Take it out, putting in a new tendon, okay? But in some cases, we actually tested some of the wires. And here's a sample out of the report where we actually see the wires, after testing in tension. And the shapes are very important because they tell us we still have a ductile system. That means the stress concentrations are not changing the type of ductile final product we have after a test. Next slide. Okay. We even set up a lab experiment and test. It's a test. It's not an experiment. It's a test where we actually took some of those tendons and we held them under stress, right, in their conditions, because corrosion is made worse by stress. Okay, so we did quite an evaluation. Okay, so quite frankly, with the peer review panel looking over our shoulders, we put a team. As soon as it was discovered, we put a team together. We got as much information as we can. Sometimes we even went out and purchased new equipment that, quite frankly, perhaps at this point had never been used for anything quite like this before, to allow us to collect overwhelming evidence. So we had a lot of information, thousands of photographs. I lost count of how many videos we took, and then we actually removed some, did some testing. Our corrosion expert, Rob Reese, actually opened one up as a high school student would open up dissect a worm. We also involved FHWA and their corrosion experts on the East Coast. We actually also had the peer review panel, external independent peer review panel with Joe Nicoletti looking over our shoulders on this. And at the end, what we had statistical information, strong engineering information, that something like 1.5% of the strands had what we termed moderate corrosion. That means we were losing about 5%, something like that, of their strength. Didn't mean it went away, just means it was reduced to a certain degree. But still, the overwhelming amount of the steel was still meeting the full ASTM tensile loads. And a few of them we actually took out, but others we actually go through an evaluation process of, do we want to take it out? And some we did, and others we go, well, you know what? When we take it out, we actually do some other damage. What's the right balance? And we went through an evaluation of how much extra do we have? And we reviewed our calculations, and we had about 10% extra pre-stressing, right? So we got like 10% extra, and that's on top of code factors of safety and capacity reduction factors. However, we did have about 1.5% that we lost something like 5% of their capacity in. But if you think about 1.5% times 5%, that's less than like 0.1%, or it's a small fraction of 1% as compared to we got 10% extra in reserve. So at that point, after we had removed some specifically and done the proper engineering evaluation, our levels of safety and our level of comfort were great. And that was a challenge, and quite frankly, without Joe Nicoletti, I think it would have been a lot harder. Next slide, please. Okay, I think we've got a pre-stressing video. Comes next.
Nearly half a mile of concrete has been poured for this section of the Yerba Buena Island transition structure, which connects the new Bay Bridge to Yerba Buena Island. The concrete is cured for a week, and already the next major phase is underway to make it even stronger.
We've just completed pouring 3 massive concrete pours, totaling over 1,000 cubic yards for the deck alone on the structure. And the next step that we're doing is installing steel to reinforce it. Concrete is great in compression, steel is great in tension. When you put them together, you've got something that's super strong. That's what we're doing now.
The plan is to snake tendons of steel through the concrete. To make that possible, engineers had to plan ahead long before the concrete was poured. Even as the structure was being framed in wood, workers were laying corrugated ducts the entire length of the deck. You can see them here, nestled beneath the rebar, waiting to be covered with the strongest concrete man can devise.
We've designed the deck so that it has grout tubes in it. These tubes will allow us to put steel tendons, on average about 26 tendons each, inside the individual tubes, and then we'll tension them to add strength. There are almost 100 different spools of strands of wire that we had to place inside this bridge deck last week as we unrolled each individual strand, pulled them about a half mile to the other side. On one end of the bridge, we had a winch that did the pulling. We took a tow line and pulled it all the way through the inside of the bridge, connected it onto the strand, and then pulled the entire strand through. The amount of steel that's on the inside of this concrete structure is tremendous. There's over 17 million pounds of steel inside this bridge. Over 21,000 pounds of it is these post-tensioning strands.
It takes about 10 days to snake those tendons through the bridge. But adding all the steel is just part of the process. They don't want it slack deep inside the bridge. They want it taut, pulled as tight as possible, meeting strict engineering specifications for each tendon. That's post-tensioning. On both ends of the bridge, jacks are being used to stretch the tendons.
They measure the amount of pressure that's on them, and then once they've reached the spec, they stop, they cut the strands off, and they cap them.
As the cables are tensed, you can see the ends start to stand erect, and while that is happening, tendon by tendon, the bridge itself begins to lift, exactly as planned.
The whole point of the post-tensioning is to add extra strength to the bridge. It adds a little bit of camber to the bridge, and the bridge starts to lift as the steel is tensioned. And you can see now we've got about 2 inches of lift coming up off on the structure. and we'll get up to as high as 4 inches.
The jack is removed, the tendon ends are cut, both ends are capped and secured. Then a final step. Each tube has to be filled with grout. Hundreds of bags of grout will be used. And even that took lots of advanced planning.
What they're clearing out here is a grout vent. After the steel tendons are placed and tensioned inside the bridge deck, the entire tube that the tendon is in is filled with grout or concrete, so that it's completely protected from any type of corrosion that would happen. But these are very important, these grout vents, because as they're pumping the grout through, you have to allow the air the ability to escape. The tendons are moving up and down through the bridge, and so as you push grout through the tendon, you need the air to be able to come out through the vent so the grout can continue on.
The same process was done on the Skyway portion of the bridge. Corrosion was discovered on some of those tendons. Coming up, we'll show you how that problem was discovered by Caltrans and what they did to fix it. On the New Bay Bridge, Mark Jones reporting.
We have a lot of structural steel on this bridge, and when you have structural steel, you need to weld it. Welding's a modern miracle. I mean, if you think about it, you're taking things, units of structure that are 50,000 pounds per square inch, sometimes ½ inch thick, sometimes 2 inches thick, sometimes 4 inches thick, and you're basically melting steel, melting it, and then connecting them, and then letting it cool down and grind it smooth. Okay? And we're doing miles and miles and miles and miles and miles of it. Okay? Well, you can't do miles and miles and miles and miles of anything without having a few imperfections in it. Sometimes it's an imperfection that it's within tolerance, it's no big deal, and sometimes it's a little larger. And we inspect it, and when we find it, we take it out. Okay? That's generally what we do. But every once in a while, then we do some fit-for-purpose evaluations. That is, if you're going to dig out the steel, is the imperfection really, is it really just better to leave it in there? It's just fine. It's going to work just fine under all the loads that we anticipate comfortably in the life of this bridge. And we call that fit-for-purpose evaluation. It's something that not only Caltrans does, it goes all the way up to FHWA. It's common practice. Or it's practice across the United States when it's appropriate evaluation. And next slide. And I'd like to ask Aaron to come up and verbally walk us through this 3-minute video.
We have to test how they're welding the structure. Just like concrete, there's a recipe for every weld that you put in a bridge. So what we'll do is we'll have a welder prepare a specimen. He'll weld it with the recipe they specified. He'll weld out that plate, and then we'll take that plate and we'll cut it up into pieces, and we'll send it up to our lab for testing. So what we're going to show is how we do that testing up in our lab. So the first test we're going to do is called a macro etch. What we do is we take an acid solution and we brush it on the steel. And what this does, you'll see that it brings out the weld in the plate. You can see every move that welder made. So what you're looking for is you want to see if you obtained a proper fusion along the edges and at the root. As you see here, he left a little something behind, and that'll jump right out at us, so we would reject this plate. The next one we're going for is the side bend test. This is a similar test. What we're doing is we're bending the plate right at the weld. So any discontinuity that we have in this plate will tear right along that discontinuity and become very obvious. So in a second you'll see, we'll roll it over and show the weld. So any discontinuity that would have happened, right there at the bend, it would have tore right open. Okay, so the next test we want to do is called the reduced section tensile test. We load this piece of the weld in a machine, and then we try and rip it apart. We want to determine what kind of strength this steel has. We want it to be stronger than all the rest of the steel we built this bridge with. So as you see here, it's tearing, and then it'll pop right at that point. So we're measuring the load it takes to break this the whole time through. The next test we do, so we're running through this quick, it's called the Sharpie V-notch test. With this test, we're trying to determine how tough this material is, how much impact it can take. We want this steel to be tough and be able to still stand an impact. You see there, a hammer drops down from a certain point with a known energy, slides through and measures how much energy it took to break this steel. And here's some broken specimens here. We want this to be tougher than the base metal that it's made from. The last one we'll do is called the all weld metal tension test. So this specimen's made of only weld metal. And what we'll do is we'll measure the strain and the stress that it can take. We want to verify that this weld metal can stretch just as much as the base metal or more. And then we want to verify that it's stronger than the base metal it's made of. We want to know that this weld metal is stronger than what we've designed this bridge for. So, and here's all the samples that we do. We do multiple tests for each one. So it's a quick run through of what we do for welding.
Thank you very much. I got to tell you, when I think of that 180-degree bend test, yes, sir. Jason, you might need to answer this.
In the beginning, he said that you were mixing your welds. Are you saying that you're using different types of welding rod to get different characteristics, or what do you mean by mixing your welds?
Yeah, that's exactly right. What we do is on a bridge, one type of welding may not be the right way for every situation. So what you'll do is, it's essentially the standard ways specified in the code that are, every time you use this combination of variables, you're going to get a perfect weld and you'll be able to walk away. That's not always the what you need to build your project. So we allow welding engineers to come up with their own recipe, but we then test it in this method to verify that it provides us with the strength we need for our project.
So you're saying you have one rod that you might lay down that's low hydrogen, and the one on top of that may be a high carbon steel?
It depends on what method he tries to use. There is a possibility of mixing methods, and then you test it afterwards.
Thank you.
I just comment on two things. That bend test, taking two pieces of steel, weld them together, and then you bend it 180 degrees. That always really amazes me. And that Sharpie V-notch test, the thing that looked like the pendulum swinging down, and it was a pendulum swinging down. It looks like a guillotine, I think. That's really fantastic. Sharpie V-notch test, and what it does, again, it provides measurements of how much energy that little piece of steel absorbs, that representative piece of steel can absorb before it fractures. It also tells us about how tough it is, and we want tough steel. That didn't get developed until the experiences of the Liberty ships sinking during World War II. So this is a post-World War II technology. So the steel on the new east spans of the Bay Bridge, it's going to be tougher than the steels that were around prior to World War II. Okay, so those two tests are really fundamental. I'd like to go to the next slide. Okay, welding gets done in a lot of different ways. Some of them are very human and some of them are automated. This is probably the neatest contraption I've seen out on the bridge. It's the buggy. It's basically looks like a little electronic go-kart set up on tracks, gets turned on. It's electronically driven. The proper voltage, amperage, all the welding requirements. It's got welding feed on it, weldment feed on it, and basically it takes the human out of it, partially. Okay, and anytime robots or mechanical things, they're very, very good at doing the same thing over and over and over and over and over again, very, very consistently. So if you can get the human element out of welding, that's generally a good thing. When we were over at ZPMC, where the box was completed on the self-anchored suspension bridge, ZPMC had purchased a bank of Lincoln welders, which a welding company here in the U.S. supplied those welders, and they put them on a moving gantry. They literally at times had 6 welding sticks moving all on this gantry down, and 6 welds were being laid down all at once. It's fantastic. Next slide. But sometimes, if it's unique and there are no robots, there are no semi-automated or automated methods. Sometimes a welder just has to crawl in a place, go sideways, get upside down, and do the welding work. Sometimes that's with a stick, sometimes that's with a grinder, and do the work. Okay, so we have all those kinds of things on bridges, and certainly this one. Next slide. Okay, and again, we inspect everything. Contractor does what we call quality control. They inspect, and then we come back with our own inspectors, QA. And this is one of our QA inspectors using an ultrasonic machine. Okay, up on the tower, the SAS. Next slide. And I always like to say a happy inspector is a good inspector. He clearly is into his work. Next slide. And then we've got an MT-UT demonstration. I'd actually like to turn up the lights, and I'd like to have you see what kind of inspection we actually do on a weld. And I'd like to have the camera on it. So,
David, my name is Mike Forder, and I'm going to demonstrate a little bit of non-destructive testing with Jason here. I'm a steel and non-destructive testing technician working with the state of California for Caltrans. And what we're going to demonstrate is a couple of different things and techniques that we do. So like we were talking about earlier, Aaron and Brian were talking about making the recipe of the welding. And what we do is we look at that and then we destroy it. We test it, we tear it apart, we bend it, we do all these different things in the laboratory. And then once we get out into production welding, we have inspectors and different people that are out there. We ensure that the recipe is being followed. So we look at that at each step of the way. And then once the production welding is done, it's in the structure and we can't destroy it anymore. We can't tear it, we can't bend it, but we have additional tools to help assure that what the recipe was followed and that we have the things that were taking place. We have two different methods that are up here. They're called non-destructive testing methods. First one we're going to demonstrate is called magnetic particle testing. And what this does, it looks for any issues on the surface or the near surface of what you're testing. So we have an electromagnetic yoke, and it creates a magnetic field. When you energize it, he pushes the button, it will come on and generate a magnetic field. And then we have iron powder that is here, and we're going to demonstrate this a little bit. So he'll energize the yoke, and he'll sprinkle these iron powders. If there's anything in between there that breaks that magnetic field, it will stand out. And then we'll be able to see it with our eyeballs, something that we couldn't see visually before. There you go. I'm not sure. Can you zoom in on that? And then, there you go. And then what's happened is he has an issue that is right there.
Can you guys see that?
Well.
Or too dark? I can make it lighter.
Go ahead and make it just a little bit lighter if you would. That's great. And this one happens to be laying right along the toe of the weld, right there. And then what we do with that, if we find a particular issue, we go to the code book and we look at the code, and then the code determines whether or not we have to repair that, and tells us what we need to do with it. The other non-destructive testing method that we have is called ultrasonics. And what it is it's high frequency sound. It's similar for when a young lady becomes pregnant. Everybody says, hey, I want to go look at the baby. And you get an ultrasound. And it is the same technology. We just don't use it on people. We just happen to use it on our welds.
Is that pretty visible?
Yeah, that looks pretty good. So what happens is we put an ultrasonic gel or something. Ultrasound or high frequency sound doesn't travel through air, so we got to get rid of the air. So he puts a couplant on here, similar when you do that on the lady's stomach. And what it is it's the ultrasonic unit will send, it will talk, it will send out the high frequency sound through what we call a transducer or a probe, and it will send this sound out. It will go. If there's nothing there, it will just continue on. You won't see anything. If there's something in the way, it will bounce back and be read on this screen. And then as he scans across, there it is. You can see right on that screen, you can see an indication, or what we call an indication, but it's basically a blip on the screen. We look at that. We see how tall that is. Again, we go back to the code book. We look at the code book and we look and see what's on the screen. We look in the code book, and then the code determines to us whether or not we have an issue that we have to take care of and repair. So we did not bring another one. We have a third method that we use. It's called radiography. And what that non-destructive testing is, the same thing as if you break your foot or if you break your hand, you go to the doctor. What is the first thing that they do? They happen to take an x-ray, and they determine if you have a broken bone or if it's just something that's done in a muscle. We have the same type of technology that we use on steel. We have a piece of film, and it goes on one side of the part. We have a x-ray generating source on the other side, and basically just like a camera, we take a picture of that, and then what we do is we develop that film just like you would normal film, and we take a look at it, and we go and we read that film, look at that film. Again, we go back to our code book, and we look at that, and then it determines and tells us whether or not we have an issue that we have to take care of. So this is just an additional step that we have that ties it all together. We have different technicians, Jason, myself, several other individuals throughout the state that Once they determine the recipe, they find out the recipe that works, that gives them engineers and Dr. Maroney the information that they need to build the bridge or to build the structure. Then we have different individuals that are there to make sure that individuals follow that recipe. And then as a final step, we have the non-destructive testing. So with that. Yeah, actually, if we would like to volunteer, you want to come up and you want to do one of these methods, we'd more than love to show you how it's going. Not sure if anybody. With the bright light in my hat, I can't see. So, okay, great. So at this point in time, we're going to hand that back to Brian. So thank you very much.
Great, thanks, gentlemen. As we leave, we're just about done. I really encourage you to take a look at the ultrasonic system. It is very, very cool. If I can get, I want to do one final challenge and success story that I think Joe Nicoletti was involved in on the San Francisco Oakland Bay Bridge. Yerba Buena Island South-South Detour, roll out, roll in. If any of you remember Labor Day a few years ago, we actually shut down the Bay Bridge and pushed out 300 feet of double-deck steel structure. One of them was One of them was about 80 years old, and the other one was brand new. And after the second evaluation of should a self-anchor suspension bridge be built or should an extension of the Skyway be built, the South-South Detour, particularly the east tie-in, found itself about 9 months on the critical path. That's not where anybody wants their sub-project. Okay? So we had ourselves a problem. What we did is we worked it into a strategy, a whole new strategy, a new design, a bold one. I think the most impressive bridge engineering California Department of Transportation has ever done. So we started out the problem. The challenge is, after that evaluation, and it was decided again, yes, the self-anchored suspension bridge is the right thing to build, we found this part of the bridge 9 months on the critical path, so we're behind. And the idea is, next slide, the existing truss is out there. We build a truss right next to it, 180 feet in the air, double-deck steel truss. Next slide. We move out the existing truss after we cut it loose. That was not an easy thing to do, and we actually started cutting the week before. Next slide, carefully. And then we moved in the new truss. Next slide. And opened up the structure in a single weekend. Next, Labor Day weekend. Okay, here's a shot of it out in the air. Okay, next slide. Shot from the air. Now it's in place. Next shot. Okay, and this, by the time we were done, because of this, quite frankly, exciting piece of work, we went from 9 months on the critical path to about 6 weeks on the critical path, which that's an acceleration in construction. That doesn't happen very often. And this was unbelievable. Again, bold. And I'm very confident I do not believe we would have got the support to do something like this without the support of Joe Nicoletti and Seismic Safety Peer Review Panel. Next slide. And finally, I think it's appropriate to end this first Joe Nicoletti lecture series, paying tribute to Mr. Nicoletti. And with that, I think if anybody has anything they want to look at, touch, let us know. Any questions? We've got our geotechnical people, our construction engineers, we've got people from design, and of course we've got our materials testing folks. Thank you for the time.
All right, thanks, Brian. And we've gone a little long, but we covered a lot tonight. So we want to thank you all for coming out. We're down to an intimate group here. So we'll bring up the house lights. If you have any questions, we'll be happy to talk to you directly. And thanks again for coming to the first of our four speaker series on focusing on business and construction of the